Hey, it's your boy Chilla here. Welcome back to C++ multithreading. In the last video, we established our problem, which is the problem of uneven loads and how it reduces the efficiency of our worker threads. And today we're going to talk about a solution to that problem. So I don't know if I already gave spoilers for it, but the solution is to use a queue. And queue is very common in multithreading. Your producer and consumer queue paradigm is a very fundamental concept. And we're just going to do a very simple queue to start off with this one, but it should be an interesting little experience. So how does a queue help us? Well, we look at our diagram here. This is what we got right now, right? We got an array or a vector of chunks. Each chunk is an array of tasks. And then we divide that array of tasks into 4 equal parts and give 1 part to each of our worker threads. So it could be 4, or it could be 8, or whatever we set it to, because we made it parameterized. So what we're going to do now is, instead of dividing it, we're just going to have, same as we already have, chunk is just an array of tasks. But now every thread, what it's going to do is, when it needs another task, it's just going to grab the first one off the top here, the first uncompleted task. So thread, well, let me just change my color here since I was using blue for the workers. So worker 1 will pull task 0, or worker 0, whatever. Worker 1 will pull task 1, worker 2 will pull task 2, 3, 4, and then when a worker finishes its work, all done, it will then pull the next task off here. And by doing this, as long as there are tasks remaining to be done, you will not have a thread standing around with its thumb up its butt, because it's always going to be pulling tasks off until there are no tasks left to pull. So how do we implement that? Well, I mean, I could, if I wanted to be fancy about it, I could use like maybe templating, or I don't know, inheritance or something, so that I could use the same worker and master control for both scenarios. But we're not gonna fancy it up like that. I'm just gonna copy. Let me just put this code up a little higher. We'll put that, I don't know, after this, I guess. So this is the stuff that's common to both. This is the stuff for our a priori task allocation. And now we'll just copy this code and paste it, and this will be where our starting point for creating our queue-based solution. So I should probably rename these classes so you don't have 2 classes, 2 functions with the same name. All right, so here we have copy pasted ourselves to completion, and we have master control queued, worker queued, do experiment queued. All the things have been renamed. Now it's time to get to work. So how are we going to implement this queue? Well, we're actually going to keep the exact same data structure. The only difference is that in master control, we're going to maintain a pointer. So we'll do an index even. Size t idx. Yeah, we'll just set that to 0 to begin with. So the idea is, for every chunk, we're going to reset the index to 0. And then as workers pull things off the queue, we increment the index and we give them the thing at the current index. So it's going to make a few things a little different. Each worker is going to see the same span. Or maybe workers don't even get spans now. Maybe they just call a function in master control that gives them a pointer or a reference. And then that, yeah. So that's what we want to do. Wait for all done. I mean, we could probably keep this the same. Signal done. Yeah, so that'll be the same. So we want, I'm just trying to think here. The master control, if it's going to be handing out references to tasks, it needs to be aware of the tasks. So let me just think here. Std span task current chunk. So this seems like it'll be something that we want to have, and then we'll have to have a function in here that sets the current chunk that we're being worked on. Wait for all done. Okay. But let's just start with task pointer to get task. Get a task. All right. And what this will do, and we're gonna do things interesting to begin with. We're not going to synchronize this access, and hopefully we can see a race condition if we play with the parameters and we get a little lucky. I don't know how common a race condition is going to be here, but we're going to try to make one happen. So what we do is we'll just do current chunk at index plus plus. But here's the thing. So if is greater than or equal to chunk size. So if the index reaches chunk size, that means that we are at the end of the queue of work. So we should just return null pointer. Otherwise, we should return current chunk at index. Why are you angry? Because it is a... Yeah, we need to return a pointer. We're using pointer so that we can, return the case where there is nothing. We used a reference that wouldn't be easy to accomplish. So this is a good use case for a pointer. We return what's at the current index, which starts at 0, and then we increment that, post increment. And this could give us, one or more race conditions. But hopefully we'll see those, and will give us a good opportunity to solve them. Now, the other thing we're going to need here is an ability to set the current chunk. So we would want, I guess, just void set chunk span task chunk current chunk is equal to chunk. That should be simple enough. It's nothing too complicated here. We'll see. We might have to change that a little bit, but seems good for now, and the other stuff remains. Okay, so now the worker. Worker die is good. Set job is not what we do. We no longer need to set the job. Get number heavy, get it. Well, that's good. That's good. Process data. Okay, so here's where it gets interesting. So while auto T, we'll make it, we'll call it pre-task. Keep with our nomenclature. While auto, when it's not in, it's while p-task is equal to p master. Yeah, we got a p master. Get task. So while we can get non-null tasks, p task process and p task heavy. There you go. All right. And that's all that needs to change in here. And then when we run no. And this should be simple too. We're just waiting. And then once we get the go signal, we're going to process until we're out of tasks, and then we're done. Yeah, see? Okay, so that was actually maybe even simpler than I expected it to be. Bool dying, number heavy, work time, accumulation, task. Don't need this one. Now, here, we work while input is not empty. Okay, so we need a way to signal to worker threads that it's time to start working. Before, the signal was when we gave them the job, gave them the span. But since there's no span to give them anymore, we signal by what? What do we do to signal? Dying, bool, finished, bool, working is equal to false. Okay, so we'll put a little flag in here. Return working or dying. So you wake up if you're working or if you're dying. Otherwise, it is sleepy time. Okay, so now we need a way of setting the working flag. So void start work. Seems like a good one. Working is equal to true. So we should do this under a mutex, right? Like this. It's basically the same as kill, almost. Except we are going to set working equal to true. And then we notify. Yeah. Okay. Start work, kill, get result, get number of heavy, get work, get job work time. Could call that get chunk work time, since the concept of a job isn't really applicable, but whatever. Whatever. We're not going to worry about the nomenclature that much here. And then, oh yeah, okay. And then in process data, we've got our loop here. When we finish, we should set working equal to false, so that we actually wait instead of just immediately going through the loop again. Or we could do that in signal. No, that's fine. We'll do that here. Or we could do that in here. Yeah, we'll do that here. Seems fair. Okay, so now we just gotta fix up our little queuing job here. So for chunk in chunk, this stays the same. Okay, so there are no longer subsets, and there is no longer a set job thing here. So what we do is we do mctrl dot set chunk. So we set a span, which is just the chunk, right? Yeah, it doesn't like it. Why don't you like that? Why can't I use a chunk? Because it's probably got to be at const. Yeah, makes sense, makes sense. I respect it. Const task. I respect you, compiler. Wait a minute, why are you still angry? Because of this. Yes, I love it. Const correctness, just hooking in my veins. Okay, so now we set the chunk. Chunk is all perfectly set up in here. Now we have to tell each worker to wake up. Auto W in worker pointers. Well, might as well keep it like that. Worker pointer to start work. So we call start work on each of those boys. And then in master control, we wait for them all to be done. And then we do our chunk measurements if that is enabled. And there we go. And everything else should actually be the same. So this was actually quite a bit simpler than I expected it to be. Now, will it compile? That's another question. Well, that must be my lucky day. Will it crash or will it hit a infinite loop somewhere? Let's see. Well, let's turn down the number of the size here so I don't have to wait for so long. Bring this down to 2,000. 50. So this should give us a lot less time spent working. Yeah. Okay, that's really fast. Result 1173. 8373. Beautiful. So we can see right now, 6983, that we are getting race conditions because we're getting different results every time. So the processing that is being done must be different. And you might wonder, well, what would the race condition actually be? And basically, well, let's look at the code. Maybe it's a little more illustrative to do it by looking at the code. So the main problem is this line right here, where indexing into current chunk to retrieve the pointer to the task there, and then we're incrementing this. So what is the race condition? Well, there are different possibilities depending on how your threads are running or your cores are running at the same time. So the good possibility is that core 1 indexes this, gets the address, then increments, so it goes from 0 to 1. Then core 2 indexes, gets task 1, and then increments. So core 1 gets task 0, core 2 gets task 1. Okay? Now, what happens when things, when we shit the bed? Well, core 1 indexes into this, gets task 0. Then core 2 indexes in here, also gets task 0. They're both now working on the same task. Those results are duplicated. Not only are they doing redundant work, which is going to make our processing slower, but because those results are duplicated, when we merge them at the end, when we add them all together, we're going to get a different result. Then they both increment. So the end index is the same. It'll still be pointing to element 2, but they've both processed element 0, and nobody has processed element 1. So that's just bad for a number of reasons. So the solution is basically we have to make the operations of indexing into the array and incrementing them, they have to be indivisible. You can't insert, another thread can't do something in between those two things. You have to make them atomic. And the simplest way you make a set of operations atomic is you use a mutex. So we're going to do std lock guard lock mutex. So we're going to lock the mutex. We're going to do it at the top here because this also could possibly be a race condition or a data race, I guess. But anyways, yeah, we'll just lock it for the whole thing here. Now, we'll run it without the race condition, and we get 6470. Let us run it again. Where's my thing? Here it is. 6470. 6470. You're going to get the same result every time because now the exact same processing is being done every time. Nobody is, processing the same element twice. Nobody is skipping elements. And that's a good thing. So let's take a look at the performance difference between these two scenarios. Run it without the lock. Takes about 5 milliseconds. Takes about 5 milliseconds. Takes about 5 milliseconds. We run it with the lock. Takes about 5 milliseconds. Takes about 5 milliseconds. There you go. So this is just to illustrate something. Some crazy people who don't know what they're talking about and should be punched think that you can never use a mutex because it will always make your program slow as molasses. And that is dumb and laughable. We laugh at those people. Obviously, whether a mutex usage is going to be a significant performance degradation depends on, you know, how often you're locking the mutex, which means it depends on the ratio of how big your individual work items are in comparison to how big it is to lock a mutex. So if your work items are decently sized, then a mutex isn't going to make a difference, and it will often be a lot easier to implement than some other lock-free solutions. So this is why your first inclination should always be to reach for a mutex, not to always think, how can I make this lock-free? Because that is that's just an amateur way of thinking, is what it boils down to. That's not how someone who has experience thinks about things. They try to do things in the cleanest, simplest way possible. Now, that being said, I would like to experiment with what size of task is like the breaking point where you start to see a significant reduction in performance when you use a mutex. So because our tasks are relatively large, use 100 iterations for light elements, and 15% of the elements are heavy, they do 1,000 iterations. That is going to swamp the overhead of using a mutex, and it's not going to matter. But let's turn down the volume a little bit here. We could start with a factor of 20. We'll make it 20 times cheaper to process a task. What do you think of that? 20 times cheaper to process a task. Now, we're going to run into measurement problems, so we should probably turn up our chunk count. Well, yeah, turn up the chunk count. And we'll turn up the chunk size so that the, measurements aren't so small that our clock is giving us too much noise. So we build that. Now let's see how long it takes with, it's good. Where's the, where did I put the mute? So let's see how long it takes with our mutex lock. Took about 1 millisecond, 1.3 milliseconds. So, I mean, we could pump up the jam a little more. Let's just 10x the chunk count. We don't want to mess around here. All right, now it's interesting. 10xing the chunk count only increased the processing time by like a factor of 3. Interesting. Anyways, so 3.6 seconds. Let's try one more time. 3.7. Okay. Now we're going to turn off the mutex locking. Remember, it was about 3.6, 3.7. 3.2. So that is 2.9. Yeah. So now we're seeing that when your work items start to get a little lighter, all of a sudden, yeah, it makes a difference. Using the mutex is giving you, I don't know, like 20% performance overhead. What if we turned it down to just like 2 iterations on the light and like 30 iterations on the heavy, and we'll just we'll quadruple the amount of chunks that we're processing. What do we see now? Okay, so 7.3 milliseconds, 9.2, quite a bit of variation there. 8, 8.7. So we got a decent amount of variation, but it's like around between 8 and 9 milliseconds. Seems like pretty common. Now we turn on the lock guard. 8. Well, Jesus Christ. All right. Well, I mean, I'm not unhappy with the situation that Mutex is actually this cheap. But I'm just like, I'm a little surprised. I was expecting it to, you know, if I made the tasks very small, then, you know, the mutex, the cost of locking the mutex every time you pull a new task off the queue would start to, you know, make things a little heavier. But I mean, well, I mean, it was like between 8 and 9 was what we were seeing. Then now we're seeing like 10 milliseconds. So, I mean, that is like, it's like a 25% overhead. Maybe. This data, I mean, this data isn't obviously the most amazing, and you have lots of variance with the way threads are scheduled on the operating system, so it's difficult to get super accurate values. But I mean, we are seeing an overhead by locking the mutex. But my takeaway so far is that it's actually even a lot less of a thing to worry about than I originally thought, and I originally wasn't a big fan of trying to make everything lock free to begin with. So this is just making the case for using Mutex even better, in my opinion. But okay, so yeah, see now, so I turned off the thing and I'm still getting these numbers. Like it's. Oh no, okay, here we go. 7.4. We weren't seeing that when we were 6.8. See, this is insane because I wasn't getting that before when I disabled this, but now I am. So I think, I mean, obviously there's a ton of variance, and we might be able to look into ways of tightening that up. But from what we're seeing here, you know, there's still a decent overhead of using the Mutex. 20%, 30%. Now I want to introduce you to something. We're not going to go into super depth on it yet, but it will be discussed later on in the series. And that is STID atomic. Allows you to use atomic types. So you don't need to use a mutex in order to achieve atomicity on certain simple operations. And because this operation that we're doing here is a very simple one, it's very easy for us to make this lock free. So, how do we do that? Well, I mean, as you notice here, we can sometimes get some pretty fast results, like 6 millisecond range, 6 point something milliseconds. But all the results every time are different, because we have a race condition. We're not synchronizing our threads. So let's try to synchronize without using a mutex. And I'm going to show you, in this case, it's actually very easy. In general, to make a lock-free, you know, data structure is often very tricky, very easy to make a mistake and not even realize it. But in this case, it's easy. So let's take a look. So we include atomic. And what we can do is it's a template. Atomic is a template. So we can say, give me, I keep losing the thing. I keep losing where I'm supposed to be looking. It's not in worker, it's in here. Yeah, so we can make this index atomic. STID atomic. Give me an atomic size t. And this will allow us to do atomic operations on that type. And the way it works basically is it abstracts the atomic part away from the specific architecture and uses the correct instructions, like something like a compare exchange, where it does two things as a single atomic operation that another core cannot access in between. So how do we do this? I don't know. Let me see. So IDX, it can be accessed just like a normal variable, but it also has a bunch of members. And what we want to do is something called fetch add, which is we want to fetch the current value and simultaneously add to that, which is what we were doing before, post increment. But now if we do it this way, it will be atomic. And It will be guaranteed to be atomic on any architecture, basically. And it's funny because some architectures don't have those atomic instructions. So for those architectures, it will actually, I think it actually uses a mutex behind the scenes then, some kind of mutex or some kind of mutual exclusion mechanism. So, but for architectures that do support hardware atomic instructions, it will use the hardware atomic instruction. So now this should just be, I'm realizing that there's a huge flaw in my code here. I don't know if anyone caught it but me. I guess probably someone has caught it already. But we should, when we set a new chunk, we have to reset the index equal to 0 on that bad boy. Otherwise, we're reusing. And because of the way, I'm just wondering, because of the way addressing works, no, it's definitely wrong. It might have even thrown like an exception or something in debug mode, but interesting. Okay, so 1 second. Okay, so now I'm interested a little bit in a different way. Let's just undo the stuff we did with atomic because this is interesting. Yeah, IDX, and we'll just make this a normal size t. We'll go back to what we had before, and we will also start using our mutex again. Now, if I run this, it's going to give me the same value every time. We probably want to increment that after we access it. Otherwise, we're gonna have a bit of a problem. Okay, so 5644. Run it again, we get 5644. So the value is stable, but I don't think it's the right value because we should have been resetting the index for every new chunk. We want to start at 0 and go up. What was happening was the index wasn't being reset, so it would only process the first chunk. And then for all the remaining chunks, it would immediately finish because it would look and it would say, I'm at the end of the chunk. So all the workers would receive null pointer at the end. So it's actually only processing one chunk, which makes the reason why when I increased the chunk count, it didn't increase the, increasing the chunk count didn't increase the amount of time spent as much as I expected it to. So let's turn this down because it's probably now going to have a very big effect. All right, funny little bug there. All right, so now processing took 650 milliseconds. So my original plan here for this video was if everything went super smooth, I wasn't going to release it as a preparatory video. I was just going to release it as the video, and there would be no prep video. Now this is a prep video, and this little foible is not going to make it into the because all the stuff that I said before is now kind of suspect. Like all the observations I made of the performance, there's a little bit of a shade cast on that because I wasn't doing what I thought I was doing. Anyways, so let's revisit that again. Now that we're fully in prep mode and we're not recording a what is the opposite of a dry run? I don't know. Whatever. Okay, so yeah, lock like this. That's 600 milliseconds. We have huge variance here, by the way. Yeah, 640. 590, 700, so much variance. It's very annoying because it makes it very difficult to compare versions. So now we run it with this. But we see a much, okay, so that is more like what I want, what I was expecting. Not what I want. Of course, I want a mutex to be as cheap as possible because it just makes your life easier. But I was expecting that when we make the task size super small, the mutex should start to have a significant impact. All right, so let's go back to our original setup. which was a light is 100 iterations and a heavy is 1,000. We take our chunk size down. We take our chunk count down. And we run it without any synchronization. 1.1 seconds. Okay. Now we run it with synchronization. And my expectation is that the difference, let's just run it a few times. 1.1. Yeah, it's going to be pretty stable now because every individual chunk is large enough. Yeah, so 1.1 seconds is when we are not doing any synchronization. And when we do synchronization, we should see it pretty close to 1.1. 1.0, yeah, well, 1.09, which is 1.1. So this, okay, so the thing I said previously, that still stands. Using a mutex, and actually, a mutex is perhaps slightly faster. Think, why would it be faster when I'm using a mutex in this situation? Think amongst yourselves, discuss. Okay, so the answer is, some tasks might be doing, some threads, workers, are doing the same task twice, and maybe that is actually making them work slower than if they were each only doing a task once. So synchronizing might be faster even than not synchronizing in this case because of the redundant work being done. Interesting. Okay. But like you saw before, if we make the tasks very light, then the contribution, the overhead of using the mutex becomes, this is about 600 milliseconds with the mutex. Without the mutex, it's like 350 milliseconds. So not quite half, not quite twice as fast, but getting close. And that is pretty much the result that I was expecting. So good thing that I caught this bug here. And it also now makes it more interesting to look at the lock-free approach here because it's so simple to do in this simple case. We make our index atomic, and now we do an atomic operation. I don't know if ++ would even, I don't know, it could be that this would actually give you an atomic operation. I'm not exactly sure, but I know that for sure. So you have compare, exchange, and you have fetch, add. These are two very common atomic operations that you do. So we want to fetch, add 1. Fetch the current value, then add 1, but do it in such a way that between fetching and adding, no other core can access this memory. It would be impossible. And now we run it, and we see it's 0.32 seconds. Why? Well, remember, synchronization actually seemed to make it a bit faster because we're maybe eliminating the redundant. Now we are synchronizing to eliminate redundancy, but we're synchronizing in a very fast way with our atomic operation. So now we get the best of both worlds. Every value, so 3300 is our value. Fuck. Okay, so apparently this doesn't work the way I thought, and I think that makes sense if you look at this. So it could be that we have a race condition at the very end with respect to this. So now we have to somehow get all atomic up in its butt. And the way we get atomic up in its butt is we do const auto I is equal to. So we do the fetch add at the beginning, do it up front here, and then we just use that index for this comparison, and we use that index here. So the memory access happens in only one place, and then that value is cached locally and used here and here. All right. Build. Okay, so now we should have a stable value. 0297. 0297. There we go. We have fixed our problem. You could see, even in this very simple example, this is the simplest example of lock-free programming that you can pretty much make that does anything. And even in this simple example, you can fuck it up. And this is so simple compared to what you would normally be doing in a more advanced data structure. But you can see here that our performance is beautiful. Almost, maybe even, yeah, pretty much twice as fast. And we get the correct result, which is also kind of important. 0297, 0297. Yeah, we are stable. We're getting the right result. And just to make sure, let's go back to the lock full version. Well, here's what we're going to do, because I'm feeling feisty. If const expr lock free enabled. But then this has to be a not a, okay, so that's, okay, never mind. Now I forgot. Let me just run it again. What was the number? 0297? 0297. Okay, so my boomer memory hasn't failed me yet, but why is it so slow? Oh, because I'm locking it and doing atomics. Okay, so 0297. And now let's go back to using a normal size T. And we'll put the IDX here, and we'll do IDX plus plus here. And a build solution. And it should still get 0297, just slower. Yeah, 0297. So the same result as using a mutex. But, go back. Give me back my lock-free goodness. Don't go back that much. You want to go with that? Yeah, there you go. Okay. But now, much faster. So that is the thing about atomic. And then when I show people this, they're going to be, oh, atomic is so cool. I want to do atomic with everything. But remember, well, actually, so we compared lock. That was a good thing, I guess. We compared not synchronizing at all to using a mutex when we had large data, we had large tasks, but we didn't compare large task in the case of mutex versus atomic. So I guess to be, how big was it? It's like 1.1 seconds, right? Yeah, it was 1.1 or 1.0908 with the mutex, and it's the same now with our locking, because the synchronization no longer matters really. The size of the task has become much larger, and so it's insignificant if you optimize the synchronization. Doesn't matter. So that's the main takeaway. Well, the main takeaway I want you to take away is that you have to synchronize this stuff. Otherwise, you will not get the same result every time. That's the whole point of teaching multi-threading. It's not difficult to create a thread. It's not difficult to access the same memory. It's difficult to do it in such a way that you get the correct result. But besides that, I also wanted to show the fact that with large size tasks, and majority of your tasks are going to be larger, it doesn't matter if you do it lock free. No one is going to care. No one is going to give you a pat on the back, especially if you do it lock free And in doing so, you make the code much more complicated and perhaps even cause a bug. That gets you fired. But there are, of course, situations in the world where your tasks just have to be small for some reason, but you still have to synchronize them. And in that case, it could be that you might need to look into atomics. And I mean, that's why I'm going to teach them. They're an important part of the process. I don't want people to get the dumb idea that I've seen so much. I've seen so many kids in high school and they first learn about multithreading and then they're like, oh, I'm a genius. I'm going to use lock 3 free for everything. It's just like, what are you doing? Oh my God. But anyways, that's just a small aside. So yeah. And I think that is pretty much, oh yeah, I wanted to do one more thing, which was I wanted to see if just your standard post increment, if this is also lock free. Let's see. I mean, if it's also synchronized. 6907. 6907. Okay, so I guess you don't even need to do. Yeah, I think this is atomic. Beautiful. One more thing I want to try. This will be interesting. What if I do it with a normal size T, but I do it like this, where I only access it at the very beginning? Is this going to be atomic? Now, of course not. Okay, that's good. That is what I was hoping. Otherwise, you'll be like, why would I fucking ever use atomic then? I just use a size T. No, of course it's not atomic. And that is, that's expected. And yeah, like I said, this video isn't, and in the main video, I'm going to say the same thing. It's not about atomic. Atomic needs its own, sort of videos because there's a lot of more complicated things about the atomic construct itself. There's a lot of things. Like you see this fetch add, it takes in a memory order, and there's a bunch of different memory orders, and it's not an easy concept, but it's a concept that I want to at least introduce when I teach atomics. And of course, lock-free programming is more than just learning how to use std atomic. There's a lot of theory that goes on to how to implement it for more complicated scenarios than this one. But yeah, okay, so cool. We can use just the normal post increment and it will do it atomically. Now let's look at one last thing. Let's see if I can coax it out here. I want to run a breakpoint in release mode here. And what we're doing, this will be fun. I'll run with the debugger attached. Okay, so that didn't work because the optimizer. Okay. We have to make it so that it does not inline. So how does that work again? Decal spec. No inline. Does that work? Build it, mother trucker. So this will make it slower, but it doesn't matter. I'm not doing this for performance testing purposes. I'm doing this because I want to look at the assembly here. This would probably be a good, better job for something like Compiler Explorer, but I'm lazy. I don't want to open up. So here we go. Here's the instruction. Lock xadd. So this is the instruction that does the magic, that does the atomic operation that gets the current value while simultaneously incrementing the value that's in there. Not simultaneously, but in such a way that they can't be separated. They can't be interposed by another core. And the lock prefix is what makes it so that all the different threads have to, or all the different cores have to synchronize on this. Xadd means exchange and add. So we're going to exchange the current value of whatever is in this memory with, I guess, RAX. And then we're going to add whatever is in EAX, which is 1. I'm sure that's how, I mean, I'm not going to look up the instruction. I'm just guessing, but probably that's how it works, right? So that's fun. Now let's look at it. What happens when we make it just a normal size t? And what I expect is you're not going to see that lock prefix there. So now we look at the disassembly. Yeah, so now you see we move. Well, wait a minute. Where's the incrementing happening? Increment. Yeah, they're just using this. I see the compiler likes to use load effective address to calculate things. So we load the current value. Then we store the current value plus 1. That's the increment. So if in between this instruction and this instruction, another core loads the current value, they're both going to be working on the same item. That's where the race condition comes in between. These two, we can have another core do something in between these two instructions. Whereas with the locked exchange and add, no other core can do something between the exchange, the loading, and the incrementing, the add. So that's how the sausage is made. In case you're interested, and I know a lot of you guys are. I know you guys get a little bit of your pee-pee gets a little hard when you look at that disassembly there and look at that assembly programming. Assembly is so cool. So, and it is cool. It is cool. Anyways, so, well, yeah, I think this video is gonna be not a mainline video. It is going to be a prepped video because of the enormous screw up that I made of not resetting this index. And hope you enjoyed it. Click the like button and see you again someday.